In this video, we will analyze a planar optical waveguide and find the maximum time a light ray can take to exit the right end. Here is the waveguide structure. The middle layer has refractive index n1 equals 1.5, and the top and bottom layers have index n2 equals 1.44. A ray enters from the left and bounces inside by total internal reflection. We label the left end as A and B, and the right end as C and D. The length is L. We want the maximum time for a ray to reach the right end. To stay inside the core, the ray must satisfy total internal reflection at the top and bottom boundaries. That happens only when the incidence angle is greater than or equal to the critical angle. The critical angle satisfies sine theta c equals n2 over n1. The longest path happens when the ray is exactly at the critical angle. Let phi be the angle between the ray and the horizontal axis. The distance along the guide is L, so the actual path length S satisfies S times cosine phi equals L. So S equals L over cosine phi. The maximum path happens when phi is as large as possible, which means the incidence angle is the critical angle. That gives phi max equals 90 degrees minus theta c. Substituting gives S equals L over sine theta c, which is L times n1 over n2. The speed of light inside the core is c over n1, so the time is path length divided by speed. That gives t equals n1 over c times s. Substitute s max to get t equals L times n1 squared over c times n2. Now plug in the values. L equals 9.6 meters, n1 equals 1.5, n2 equals 1.44, and c equals 3 times 10 to the 8th. This gives a time of 5 times 10 to the minus 8 seconds, which is 50 times 10 to the minus 9 seconds. So t equals 50. Therefore, the maximum time to exit is 50 times 10 to the minus 9 seconds, so the blank is 50.